So we are starting section 1.5 on graphing trig functions. We said the most basic way of graphing functions is point plotting. So if I want to graph a function y is equal to, say, sine of x, a basic approach I can have is to make a table with values of x and y in it, and for each pair of values here I can go ahead and find a point in the Cartesian coordinate system that corresponds to it. So that's our general approach. Find an angle, or pick an angle, find its sine. We get a pair of numbers. Those pair of numbers become and plotted here. The first issue is that for measuring angles we have a variety of units. We could measure in degrees or radians or grad. We have to make a choice based on that. And our numbering on the x-axis is going to be different depending on the units we have chosen. The shape will be the same, just the numbering will be different. So to go after a problem in more familiar fashions, perhaps we choose degrees here first, and then second time around we go around and do the same thing with radians. Next, we have another choice. You want to pick your angles here and find their sine. Of course, there are infinitely many angles you can choose. Which one do you want to pick? If we choose just arbitrary angles, then we have to resort to some other mechanisms such as calculator or graphs to help us. If we choose our angles to be among those famous angles we have studied, we can bypass a calculator and try to do it by hand, perhaps, at least some of it. Now, it all depends on your choice how you want to go about it. For example, you can start with those famous angles, 0, 30, 45, 60, 90, and then going on based on these type of angles and find out what their sine happens to be, and then go ahead and graph them. So that's one option. Sticking with these well-known angles, figuring these things out, and then graphing them. Sometimes you don't want to just hang around this type of angles, so you'll be resorting to other facilities. At least you can always use your calculator. Remember, we didn't allow use of graphing calculator because we want you to understand exactly how this thing comes about, as opposed to just pressing a button on that calculator and getting the picture out. The one reason the graphing calculator were not allowed was that, well, if they were allowed, I wouldn't know what is it that you're doing, you're pressing a button or having done the whole work yourself. Anyway, so here we come and figure out what is sine of 0 and sine of 30 and sine of 45 and sine of 60 and so on, sine of 90. Now these quantities, we had worked them out before. Let's see if we remember them. For example, what is sine of 30 degrees? Sine of 30, half. This is a half, or you write it as 0.5. How about sine of 45? So sine of, here are the exact values. We had worked this out before. We had actually recommended that you memorize this triangle, which had 30, 60 degree setup in it. We said if you remember this is 2, 1, radical 3, your life would be a lot easier with respect to figuring out quite a few quantities by just memorizing this picture. Anyway, sine of 30 is opposite to the hypotenuse, becomes a half of 0.5. While I'm on the same picture, I can also answer what is sine of 60. What is that one? Opposite over radical 3 over 2. Of course, we need the decimal value of these things for graphing purposes. What is radical 3 over 2? You can use your calculator or you can memorize. So what does your calculator say? Radical 3 over 2. 0.86. You want to also make sure you get the same answer, but just in case you forget this thing somehow, you can just press sine of 60 and get your answer anyway. Okay, you can get the same thing. So I have 0.86 here. Now, for 45, we had a different picture to memorize. For 45, we had this one. If this is 45, so is the other one. And in this case, one set of numbers you could remember or memorize 1 radical 2. So sine of 45 becomes opposite to hypotenuse. We had another form of the same thing. Again, on your calculator, either you can enter this or just directly sine of 45, and you will get what, 0.71 or something? Is that right? So 71 or 72, whichever. 71. Okay, for 90 and 0, it becomes a bit more confusing as to what it is. But perhaps you remember what sine of 0. 0. Here is a funny looking triangle I'm going to draw here. The 0 angle, 0 means well, the angle hasn't opened. So we have to exaggerate to show something. So that's why I call it this funny triangle. This is 0. That means this angle hasn't opened yet. So the side opposite of that should be what? 0. These two, hypotenuse and the side, are the same because the angle didn't open yet. So what would be their measurements? I can just put 1 and 1 or 2 and 2 or whatever. So if I ask myself what is sine of 0 in this picture opposite to hypotenuse, 0 over 1. And you shouldn't get confused as to what is 0 over 1. Suppose you have $0 to give to one person, that person still has $0. This is 0. Now if this is 0, how big is this other angle? That has to be 90, is that right? In all of our pictures, this is our right angle here anyway. So if this is 0, that has to be 90. Again, this is a funny triangle. This side really right on top of this side, hypotenuse and this leg are the same. Anyway, sine of 90 is opposite to hypotenuse. And what is that? 1 over 1 is 1. So let's get going with drawing the picture. We say we want to draw this picture, and I need 0 to 90 degrees at least here. So this is 0. To open up the picture, I go far away and assign somewhere to be 90. But don't go according to the style that you had in college algebra, because in college algebra you say 1, 2, 3, and of course in that style 90 is not going to fit in your page. So you go do it the other way. You assign it 90, and then you say, well, halfway point of it has to be what? 45, and a third of it has to be 30, and 2/3 of it has to be 60. So we kind of fit the largest angle we want to look at in our page first, and then decide according to that as to what the other points are going to be. We typically don't see 1, 2, 3 in this type of a picture because those angles are just so small. They don't really show up. On the vertical axis, when we are dealing with the sine function is, after all, is the ratio of a leg to the hypotenuse. So that's going to be at most 1. In the negative cases, it's going to be at least minus 1. So on the y-axis, we make sure that we can show 1 on our page. We don't need to go above that, and of course we don't need to go below minus 1 either. Notice that the unit here has nothing to do with the unit here. These are two different stories, not to be confused. So we are not going to insist that if this is 90, then that 1 has to be a tiny little tick mark here. That's doing its own thing. Okay, what are the easy numbers here? At 90, of course, I have sine being 1. So I have this type of point. Another easy point is 0.5. At 30, here's half of this. At 30, I have made it halfway. At 45, I've gone up to 0.7. Now, it becomes nitty-gritty detail of this. Are you using a good graph paper or a good ruler to make sure exactly how things are going to look like? So we need to have really decimal numbers here. 0.5, I need 0.5, 0.6, 7, 8, 9, 10. So you do really need to divide this thing at least to 10 pieces and be able to differentiate between those 10. So you go from your 0 to 1 and mark it to 10. So this is 0.7. 0.71 would be about the same location. So I come here. This is 0.71. At 60, I have made it all the way to 8.6. So this is 7, 8, 8.5. So notice it's not a straight line, it's kind of curving up. As we come to 90 degrees, this is flattening out. So we get a picture kind of looking we are graphing y is equal to sine of x. Now, the situation becomes more interesting. So let me write this in. This was 0.5. It's radical 2 over 2. This was radical 3 over 2. And this is, of course, just a 1. In our picture, we don't want to just stay at 90 degrees. We want to keep going. What happens if I continue with my table? So, okay, here let's continue with this table. I'm not staying at 90 degrees. I want to keep going. So I say 90. I want to go all the way to 180. 90 is just my 90 here. At 180, what are we going to do here? So for angles larger than 90 degrees, we have to resort to our coordinate system and unit circle. So I go ahead, I devise this method of handling all of these angles. I draw a circle of radius 1. You remember that we had put marking for this 45, 30, 60, and this was of course 0 and 90. This was 0, 30, 45, 60, and then 90. Well, I go and put tick marks for the same angles in the second quadrant. That is, I pass 90 by 30 degrees. Where am I going to arrive at? That's going to be what? 120. And then past 45 degrees, I'll be at 135. Past 60 degrees, I'll be at 150. These are not drawn well. And finally at 180. The issue comes up to be quick in finding the sines and cosines of these things and not to spend so much time. Again, you always have your calculator available to you. You can do it, at least double check on that to make sure you're not picking up the wrong number. But the issue is, can we visually quickly draw what this sine is without resorting to just any technology around us, without resorting to any calculator or anything of that sort? So let's pick one of these angles, see what happens. Suppose I am dealing with 30 degree. 30 degree, I draw this right triangle. This is the 30 degree here. This triangle is special because the hypotenuse of it is 1. If you want to get the sine of 30 degree, you would have said opposite to the hypotenuse. Now, opposite is the y coordinate of this point. Sine of theta, you remember, we had the following definition for it, is opposite over the hypotenuse, but in general it's a y coordinate of that point divided by the radius of, or divided by the distance from the origin. Now if we picked our circle to be unit circle, our radius becomes 1, and we don't even have to worry about division, because y divided by 1 is just y. So when I want to ask about the sine of this angle, I simply can refer to this height. Okay, to say this sine is this height, which happens to be what? Which happens to be 1/2. Now I ask myself this question: if I go the other side, how different would that be? If I'm here, this is 30 degrees before I go down to straight line. This is also 30. So what's the relationship between sine of 150 and sine of 30? After all, I have to take this y divided by that r. Our r is always 1. What's the connection between the y on the left and y on the right? They are the same thing, because both cases we have 30 degrees to go before we hit the horizontal. So sine of 150 is same as sine of, so let me write down these angles here. From 190 I go to 120, then I make it to 135, then I make it to 150, then I've made it to 180. At 150, our situation is a mirror image of whatever it was at 30. At 150, situation is exactly the same as one at 30. So here the answer is again 0.5. How about at 135? So, yes, let's see. At 135, situation is a copy of whatever we had at 45. So at 135 and 45, the answers are the same, 0.71. How about at 120? At 120, our situation mirrors exactly what happened at 60. At 60, what was the deal? It was 0.87, and here is the same thing. How about 180 itself? 180 mirrors which angle? 0. At 180, we have same answer as we had. So if I continue after at 180, and then we have this half point of these 2 points is 135, and here's 1/3 here. This is going to be 120, and this is going to be 150. 120 and 60, they mirror each other. At 120, I come up as high as, let's see, at 120, I come up same height that I came at 60. At 135 and 45, I copy these two. At 30 and 160, excuse me, 150, I copy them as well. At 180. So what happens is that if I kind of put a mirror at 90 degree on my picture, the right of this is a reflection of the left of that. And so the picture starts going down and goes and hits 180. So this is a perhaps primary piece of this curve from 0 to 90, and from 90 to 180 it just descends. Now how can we quickly come up with this picture? If you play a little cartoon in your head, you can do the same thing quickly without really bothering with any of these numbers at all. If you want to just get the qualitative picture, you say, okay, draw a unit circle. For each angle, so here you have some angle theta. Since the hypotenuse is 1, sine of theta is just the opposite side. Y is sine of theta, because I have to divide y by 1 to get sine of theta, but y divided by 1 is just y. So I look at the opposite of any angle. I say the opposite. First it starts at 0, gradually comes up until it reaches 1. So here 0, I start at 0. Then I gradually come up. These lengths are the same as the length that we see here. Then after that, I start going down. 120, 135, 150, but I don't have to stick to these particular numbers. I just see that as the angle increases past 90 degrees, this height is shrinking down to 0. I ask myself, perhaps I can follow this trick and not to go after this type of nitty-gritty detail that I see here. Suppose I want to go to the third quadrant. What do I see happening to these heights? They are getting longer, but something about it is different than what you had over here. How is y up here and y down here different from each other? These are negative. So that teaches me a lesson. So, okay, you want to keep going, no problem. So we keep going on this axis. So after 180, the principal number to get to is, of course, what? It's going to be our 270. And I can put these same numbers here. Like after 180, I can go 30 more degrees and make it so I can past 30 degrees, make it to 210, and past 45 degrees, make to 225, past 60 degrees, make to 240, and continue the story with the same style that we had. But what if, I know, I'm in a rush, I have lots of other stuff to do, I don't want to pick these numbers like picking fleas or something. We just want to be quick without it. We say at 270, where am I going to hit here? At 270, 270 is down here. How tall is this? It's -1. So I'm going to hit to -1. So if I want to be quick, perhaps I just try to be more selective with respect to my angles. 0, 90, 180, 270. Then I know exact same numbers that I had here are going to show up, except that they are going to be negative. Like at 210, I'm going to be -30. At 225, I'll be same as minus what I had for 45, and so on, until I hit -1. So this is point -1 down here. Now I ran out of room here, but let's just go ahead, redraw this picture, and this time allocate our angles more wisely than I did over there. I didn't listen to my own advice. What if I want to go like, if I want to go around the circle once, I need to make room for 360 degrees. So halfway point of that would be 180, halfway point of that is going to be 90, and here's a 3/4 of that, which is 270. And let's assign some 1 and -1 here. Let's just go with the principal points. At 0, I have 0. At 90, what do I have? 1. At 180, what did I have? 0. At 270, -1. At 360, I'm marching back to where I started with, and my heights are shrinking back to 0. So they are negative and coming back towards 0. So what kind of a picture do I get? I remember to let my hand to kind of swish through these things and not make a zigzag corners and such. It is a nice curve actually. So you try to draw a curve. The best you can. So here you get your y equal to sine of x. We started at this, and the shape after 360 degrees repeats itself. That is, if I pass 360 and come back to the first quadrant, like 390 and 405 and 420 and so on, same picture shows up. For that reason, we are going to have a name for this thing. We say this picture repeats after 360 degrees. I call that length after which everything repeats. I call it a period. The period of this picture is 360 degrees, meaning picture repeats after every 360 degrees. Just like the tile patterns is what they use. After so many feet, whatever pattern that you had is going to repeat. If you want to do a tile work without repetition, it's substantially more expensive and like custom order and stuff like that. For simple things, you want repetition, and the length you go before you repeat yourself is called the period. All trig functions have a period, because after all, you go around the circle and somewhere or another you are going to repeat yourself. The period for different functions are going to be different. We are going to study that later on. Now let's go ahead and say, let's show 2 cycles or 3 cycles of sine function. So I might ask to graph sine of x from minus 180 to say 540. So now we have to make room on both sides. I try to go with some reasonable length so that it fits on both sides. Let's say this is my minus 180. This is 0. So that makes 180 to be here, 360 to be here. 180 more makes it 540. We need to kind of memorize the so-called fundamental cycle. So this might be referred to as one cycle of the whole picture. The picture essentially repeats itself. So you draw one cycle of it. Let's say this is your 1 and minus 1. So you put your marking so you help your hand. Excuse me, at 90. I made a mistake here. Let me correct myself. So this is 90, 270, 450. This is minus 90. What was the height that we are supposed to arrive at 90? 1, is that right? But 270, I make it to minus 1. At 450, what do I make? Back to 1. What do I have at minus 90, you think? If you are in doubt, you quickly draw a unit circle. That's the advantage of unit circle. Instead of fumbling with a calculator, so here's my unit circle. Where is minus 90? Here's minus 90. What's my height here? Negative 1. Essentially, you do that in your head. Otherwise, if you have to draw it, calculate it just as fast. You have to draw it in your head. So next, you say Well, how about what happens at 0? 180, 360, 540, minus 180. So what is the picture going to look like? Obviously, I'll come down here, go up, and wind through. So I'll have so we get this graph of sine of x. We limited our domain to a particular set of numbers. You see the appearance of this thing that looks like a wave. So you can suspect that these trig functions get to be used in the study of all sorts of waves. It could be ocean waves, or it could be electric waves, or light, or whatever it is. All those type of situations get to be resolved or displayed or explained using these type of functions. Okay, this is sine of x. You remember this was the period of it, or one fundamental cycle of it. Period was 360. This we are going to refer to as one cycle. You could start one cycle as at any place until you repeat the pattern. So if I start from maximum to maximum, that's going to be another way of referring to one cycle. Just don't make the following common mistake. If this is 0 and that is 0, does that mean that the cycle has repeated? No, this is a 0 at which you are coming up. This is a 0 at which you are going down. So this and that don't form a period. You have to come to the point where the overall trend is the same. Like this was 0, you are coming up. This is 0, you are still coming up. So from here to here is a period. From here to midpoint is not a period. So this is also one cycle. Some segment of this thing might be referred to as a fundamental cycle. For example, from here to here might be referred to as a fundamental cycle. So to recap, how do we graph a trig function? Really the most useful tool is unit circle. We say on unit circle, we remember the following fact. So if I have an angle theta, this leg in front of it is sine of theta. So in your head, you play a cartoon. As this angle opens up, the leg in front of it goes through a motion. So 0 gives 0, 90 degrees gives you 1. You go past that, this is your angle, this is your sine, this is your angle, this is your sine, and 180, you make it here. You pass 180, you are entering negative territory. So you keep playing this picture in your head. You convince yourself that as you go around, if you plot your angle here and plot these vertical lines above it, you get this kind of a wavy pattern. So sometimes you might refer to this thing as a sine wave. Okay, how about cosine? Same story, slight modification, but it's really the same. So we are going to go after y is equal to cosine of x. We saw the advantage of unit circle. Again, you have two options. Go ahead and make a table for yourself and patiently find numbers, perhaps using calculator, and then plotting them. So that's point plotting. All that it requires is patience, and perhaps a calculator. Okay, all that it requires is patience. You sit there and do that patiently, you get your 10 points for having done it. But you want to go one level higher up, you say, okay, if I'm really going to be an engineer, want to work with these things quickly. I don't want to take forever to figure out what's the sine of x looking like. And I want to understand it myself. I don't want to delegate it to a calculator. I say, okay, here's what you do. If you had an angle here, so here's our angle. What would you have done to get its cosine? You would have asked for the ratio of the adjacent to the hypotenuse. Luckily, if you are using unit circle, it means hypotenuse, which is the radius, is equal to what? Is 1. So that is a tremendous relief, because if we want to take the adjacent and divide by hypotenuse, you don't really need to do any more division because you're just dividing by 1. Next issue, you say if I have dealing with this unit circle, the adjacent that I'm using is just the x coordinate of this point. So if I want to draw it where the angle is, if I want to see cosine of theta, that is the cosine of theta. Length of that, if I want to have some visual impression of what the hell is this cosine, here is this. So here is, if you draw me an angle, I go here and say this is the cosine. You draw me this angle, I say this is the cosine. You draw me this angle, I say that is the cosine. You draw that, and so on. You draw an angle bigger than 90 degrees. What's the cosine of it? Just go straight to the vertical line. You draw it bigger, straight here, draw it here. So if you play this cartoon in your head, you can quickly figure out what the graph is going to look like. Let's see if we can actually do it. Let me make my axis so that this is like my 360. So that's going to be what my 180. And here are the critical numbers, 90 and 270. So whatever our picture is, we make sure there is at least a span of 360 degrees on it for these basic pictures. Now I say, let's talk it out. I start at 0 degrees. I start at that 0 degrees. How long is this horizontal line? Let me draw again. It's kind of, it's so simple, it's confusing. It's you remember, these horizontal lines are the cosines. Now I open a 0 angle. So let me exaggerate a little bit so that you actually see that I'm opening something. So I've opened something close to 0. So cosine of it is this line. Approximately how long is it? It's approximately the same as the radius of the circle. Is that right? So when my angle is close to 0, my cosine is close to what? 1. So at 0, what's my cosine? 1. So at 0, my cosine is just 1. Now I hope I didn't lose you on that. So let me go to the previous argument that we had, which was based on, well, I erased it here. Let's do it again. We said there are some famous angles we try to memorize. One of them was this 30, 60, 90. So this is 30, this is 60. If you want to go off of your memory, what were the assigned numbers for these legs? 2, 1, and radical 3. So for example, if you want cosine of 30, you say radical 3 over 2. Cosine of 60, you say 1 over 2, if you want to go that way. Now for this particular strange looking triangle, so for 0 degree, we have to kind of open it up. So this is my funny angle. This is 0 degrees. So what is the other one? 90. What were the numbers that we assigned to these? It was opposite of 0, will be 0, and these two other guys will be 90. So if I ask for cosine of 0, what's the ratio of adjacent to the hypotenuse? 1. Okay, so this is one way of memorizing and not getting confused between a sine and cosine. So cosine of 0 becomes 1 over 1. That is one style. You have to actually have redundant styles, so all of things consolidate in your head. So, okay, here if I have small angle, how do I get the cosine of it? I'm supposed to come horizontally to this axis. So how long is that? About 1, is that right? If I had 0, I'll come right back on it. The length will be just 1. That's how it happens. Okay, as the angle increases, what happens to the cosine? See, as this angle increases, what happens to this cosine? Decreases. All the way until I come close to 90 degrees. When I'm close to 90 degrees, how long is this horizontal line until I hit the y-axis? What is that? That is 0, is that right? So at 90 degrees, my cosine is going to be what? 0. That's one way. Another way is a cosine of 90. I could talk it out of this picture. Cosine of 90 is adjacent to the hypotenuse, 0 over 1, just like we said before. This is 0. So at 90, I hit 0. Okay, now I go to the angles in the second quadrant. If I am here, what should I watch out for? This length is going to be negative, is that right? Because I'm on the left side, I'm measuring this. This is really like an x coordinate. So from 1, I have descended to 0. What do you think is going to happen later? As my angles get bigger, I have to go through these lengths. What should I watch out for? Like for example, at 180, what's my cosine? Exactly, at 180, I have hit negative 1. These are actually all negative length, so I know I have to come down. Now suppose I keep going until I hit 270. What is it that I'm tracking in my head? I'm tracking how long these green lines are going to be. But where are they going? Start from 180, I'm marching back toward to 270. That is what happens to me. Okay, so these length here are copy of these length here. These green length are copied over here. Now I enter the fourth quadrant. In fourth quadrant, what happens? So let me open the angles. I keep marching toward 360. I'm supposed to calculate my cosine. The cosine in this case is all these horizontal lines. Where are they headed to? 1. That is, I copy these things at the appropriate angles, and what I get is the rest of that picture. So the graph of y is equal to cosine of x over one fundamental cycle, or one period of it, is this. Again, just like the sine function, from here to here is what it takes for the picture to repeat itself. So here we call it the period, and that period is 360 degrees. Now let's go ahead and graph this thing on something a little bit longer. Did I go quickly here? Suppose I ask you to graph cosine of x from minus 360 to plus 360. So, okay, let's allocate some room for myself. Minus 360 to plus 360. So here's my 180 and 90, 270, minus 90, minus 270. So this is 180. This is my 180 here, 90, and 270. So I make sure my picture horizontally going to fit in the page I have. So I go the highest number and the lowest number, make sure I have assigned them reasonably. On the vertical axis, we typically have enough room, so we just allocate something so that the picture doesn't look too small. So on the vertical, 1 and minus 1, the units for them is different than what you see on horizontal. Now we go and mark some fundamental points. In most problems, your fundamental points are 0, 90, 180, 270, back to 360. You make sure you take care of those and make sure everything else follows their lead. So at 90, what am I supposed to see? What would be the cosine? 0. 180, hit negative 1. 270, come back to 1. 0. And then made a mistake there. So on the negative side, what do you think is going to happen? Well, if you go 180 or you go to minus 180, same point on the circle is going to have same cosine. So at minus 180, our picture has to be copy of whatever it was at 180. So at minus 180, what am I going to have? Negative 1. At 360, positive 1. So here's how picture is going to go. So that is a graph of y is equal to cosine of x. It is drawn between minus 360 to 360. So that makes 2 cycles of it. Now when we come to the other functions, tangent and so on, we have one new complication, which is the presence of asymptotes. Tangent is a ratio of sine to cosine. When you calculate the tangent, tangent can easily become infinity. Tangent is a ratio of the opposite to the adjacent. Opposite can get to be substantially larger than the adjacent. So tangent can go to infinity. And that's going to create new problems for us. You want to study the notion of asymptotes. I'll talk about that next time. Asymptotes arise out of division by 0. We said in elementary school, they said don't divide by 0 and so on, because that's like playing with matches. But eventually you have to, and you need to grow up. So we are going to deal with that next time and talk about tangent and other trig functions. That's going to close the case. So make sure you study this section. It is rather extensive.